So this time we have a quasi-local seminar. Raman will be joining us in the next academic year in the PME building. He is interested in entanglement, topological order in general, and he has been looking at open quantum systems more recently, like how one can understand topological order in the mixed states. And he will tell us about topological order and dynamical constraints in open systems.
Thank you, Prashant, for the introduction and for the invitation to speak. It's a pleasure to be here in Chicago. Yes, I'll be here today and most of tomorrow, but if I don't get a chance to talk to you then, I'll hopefully see you in the fall. So today, as Prashant said, I'll be talking a bit about some recent work we've done in the context of understanding states of matter and also dynamics in the context of open systems. So these are many-body states which are coupled to some large environment or thermal bath. And the goal is to understand the extent to which we can have some non-trivial physics in the context of these systems. So just as a broad outline, I'll start off by giving a brief motivation about why we want to care about these open systems. And then in the two parts of the talk, I'll first talk about how we can study certain kinds of new phases or states of matter that we can obtain in these open systems. Specifically, we'll be looking at generalizations of topological order. So these are states of matter which in closed systems exhibit anyonic excitations. And then the second part, I'll switch gears a little bit and talk about how we can understand non-trivial dynamics in the context of these systems by extending certain non-perturbative constraints known as Lieb-Schultz-Mattis theorems. So these are sort of like two complementary parts about understanding the properties of these open systems, but in some broad sense that I'll explain, we can think about these as using symmetries to constrain these states and these dynamics. So before jumping in, let me just thank my collaborators. So the first part was done in collaboration with Abhinav Prem, who is a postdoc at IAS. And the second part was done in collaboration with Kohei Kawabata, who is now faculty at Tokyo, and was the main driver of the second part, and with Shinsei Ryu, who I think many of you are familiar with. So to start with a bit of a motivational preamble, in recent years, there's been significant progress in the development of so-called quantum simulator platforms. So these are a range of different experimental platforms ranging from ultra-cold atoms and optical lattices to these superconducting qubit architectures for quantum computers. So part of the interest in part of the interest and the reason for why these are called simulators is that these are highly tunable experimental platforms where the hope is that one can engineer interactions and Hamiltonians which could effectively simulate model Hamiltonians which are of interest, say, for solid state applications. For instance, one might hope to simulate, in some sense, the Fermi-Hubbard model in these systems and shed light on these models which are impervious to analytical treatments or difficult to treat with classical computers. So this is one overarching goal in the pursuit of developing these platforms. But in recent years, there's also been a growing interest in viewing these simulators as interesting physical platforms in their own right. So although one can think about engineering Hamiltonians in these systems, many of these platforms are in some sense inherently non-equilibrium in nature. So rather than thinking about simulating Hamiltonians in the context of, say, these superconducting qubit setups, what one is really doing is applying some sequence of unitary gates, potentially interspersed with measurements. So in some sense, one wants to think about these quantum systems as being inherently driven quantum systems. So there's a potential of realizing inherently non-equilibrium physics, which is outside the usual purview of traditional condensed matter. So in particular, in recent years, people have been looking at, say, entanglement dynamics and scrambling of information in the context of these systems. The second aspect is that due to this connection with quantum computation, these simulator platforms motivate thinking about traditional many-body states from a quantum information perspective. So in particular, there's been several realizations, but as one example, Google has recent evidence for realizing the Tori code topological order in their superconducting qubit system, and have evidence for being able to braid non-abelian anyon defects using these unitary gates. So the overarching picture is that these simulator platforms provide interesting settings in which to investigate traditional condensed matter physics, but also these new inherently non-equilibrium phenomena. But with that said, there's no such thing as a free lunch, and one has to keep in mind that many of these systems are inherently open. That's to say, there's some unavoidable coupling of the system to some large environment or thermal bath. And so generically, even if you start with some interesting pure state, the coupling to the environment will inevitably result in the system becoming a mixed state due to the coupling with the environment. So heuristically speaking, you can think of the system and environment coupling as resulting in over time the system becoming entangled with the environment, and by monogamy of entanglement, the constituent parts of the system will lose entanglement with one another. So for generic couplings to the environment, you expect that at late times, you'll get some classical mixed state. So at this level, it seems like decoherence induced by these environmental couplings is inherently a bad thing, since you lose this quantum coherence that you're interested in, which is what gives us interesting many-body physics in general. But when life gives you lemons, you can either try to throw the lemons back, which is in a sense what error correction is, so that's to say you can try to mitigate the couplings to the environment, or you can try to make lemonade, which is the perspective that we adopt. So the idea being that this decoherence is inherently a non-unitary phenomenon. So at least as a matter of principle, you could imagine that you could engineer dissipation or decoherence to stabilize in some loose sense many-body patterns of entanglement, which are not naturally realized in the ground states of local Hamiltonians, which are the usual objects of study in, say, condensed matter physics. And so there's actually been quite a bit of extensive literature in pursuing this kind of perspective. So many years ago in particular, it was realized that you could use engineered dissipation to essentially extract entropy from the system so as to stabilize interesting pure states as a steady state, as opposed to a mixed state. So in particular, you can engineer interesting steady states as being these symmetry-protected topological states, which are useful for, say, quantum computation applications. In recent years, motivated by these simulator advancements, there's been interest in understanding how decoherence can induce interesting entanglement transitions when you start with some interesting many-body pure state. And more recently, there's been recent progress in understanding the extent to which you could realize, in some sense, genuinely new phases of matter in these mixed state settings, which do not have pure state analogs. And so this is one of the directions that we're going to discuss in this talk. So, in broad terms, what these open many-body systems sort of prompt us to ask is whether we can realize new states of matter in these mixed state settings, and if we can realize interesting new kinds of dynamics. And given that, the natural question is whether we can, in some sense, classify these different states or different kinds of dynamics. And so in this talk, I'll present two projects attempting to carve out some new understanding in these directions by extending established frameworks in the context of traditional condensed matter, based namely on the context of symmetry. So to be more specific, in the first part of the talk, as I mentioned, we're going to be looking at generalizing the notion of topological order to this intrinsically mixed state setting. And so as a brief preview, what we're going to do is start with standard topologically ordered phases and apply certain decoherence channels to them, which, as we'll show, has the interpretation of effectively projecting out certain anyons in the theory to generate a new intrinsically mixed state. And in the language of symmetry, if you're familiar, you can think of this decoherence as breaking certain exact one-form symmetries in the state. And the second part of the talk, following this symmetry-based perspective, and we'll shift gears a little bit and talk about the dynamics in these open systems. And what I'll try to argue is that we can impose non-perturbative constraints on these dynamics in the spirit of these so-called LSM type theorems to constrain the relaxation dynamics. So that's, in broad terms, the sort of outline of the talk for the rest of the time that I have. So let me just jump into the first part. So as I said, this was done in collaboration with Abhinav Prem, but let me just mention that there's also some independent work by Tyler Ellison and Meng Cheng addressing the same problem, so you should keep an eye out for that. But so just to start from the basics to set the context, in 2D traditional condensed matter, some of the most exotic phases we know of are these so-called topological orders. So these are 2D gapped phases of matter which support fractionalized anyon excitations. So physically, this means that if we have two of these point-like excitations, A and B, and braid one around the other, we pick up some non-trivial Aharonov-Bohm phase. We put these topological orders on a manifold with non-trivial genus, say a torus. We further have the fact that they support a non-trivial ground state degeneracy, which is generated by the algebra of the non-contractible Wilson loops of the anyons. So in this more modern symmetry-based language, if you're familiar, one says that the closed Wilson loops of the anyon generate these one-form symmetries, and this ground state degeneracy on the torus corresponds to spontaneous breaking of these one-form symmetries. So although it's not critical, that language of symmetry will be useful for couching some of the following discussion. And so on a technical point, it's believed that we have a full classification of these topological orders based on these mathematical structures called UMTCs. the details are not so important aside from this modularity constraint. This tells us that if we have one anyon A in the theory, there's at least one other anyon in the theory that breaks non-trivially with it. So every anyon is detectable. That seems like a technical assumption, but as we'll see, by relaxing this, we'll be able to generate new states in this mixed state context. And so in the context of these quantum simulators, these topological orders are interesting in that they serve as error correcting codes. What that means is that because we have this topologically protected ground state degeneracy on the torus, we can, as a matter of principle, store logical information within it, which is protected against local errors. So with that context, it's natural to think about these topological orders in an open system context to see the extent to which that notion persists in a mixed state. In particular, it's natural to ask whether we can, in some sense, get a new kind of topological order in these mixed state settings. And so I should say this is a non-trivial question, since the natural mixed state you might consider is the Gibbs state or the thermal state, which we know in 2D does not support topological order. Any finite temperature results in proliferation of all anyon excitations and immediately destroys the topologically ordered ground state. So one has to be a bit more creative in how you generate potentially interesting mixed states. And so I'll say that in the past year or two, there's been some recent progress in looking at specific instances of what appear to be intrinsically mixed state topological order. But as of yet, there does not appear to be a consensus on a systematic generation or classification of these states. So what I'll try to argue in the following slides is that we're able to generate and partially classify our large class of what we call intrinsically mixed state topological order, or MTOs. And the framework that I'll outline for how we do this is we're going to start with some regular pure state topological order. For abelian states, these will correspond to some lattice models called stabilizer codes. And we're going to, as I said, apply some decoherence process, which has the interpretation of gauging out certain anyons in the theory. What we're obtaining in the end is some mixed state, which for abelian theories corresponds to something called a subsystem code. And as I'll show, these mixed states exhibit non-modular topological order. So these are these are TOs which break that modularity assumption. And these are interesting, as in the pure state setting, those kinds of TOs can only be realized on the surface as anomalous surface states of a higher dimensional theory. So these are intrinsically mixed, as we'll see, in the sense that we realize surface physics in 3D in the context of a 2D mixed state. So in the following slides, I'll outline the general picture of how this works and then discuss some specific examples to hopefully make the physics a bit more concrete.
Is it believed that all versions of mixed state topological order will correspond to purify sufficiently some more conventional topological order largely pure state?
So I think that's not known as of yet. So these are the natural things you get through this procedure, but as a matter of principle, there might be something more exotic, but people haven't found this as of yet, I think. Yeah. Right, so as I said, to outline this construction, we're going to start concretely with a certain set of lattice models. So these are called polystabilizer models. So just as a brief review, the idea is we start with some translationally invariant lattice and place some D-level system, in this case just qubits, say on each edge. We then construct local operators, which we'll call stabilizers, out of local Pauli operators on each edge. So for instance, here I'm using the example of the toric code where we have the standard Plaquette and star operators. So using these stabilizers, which we take to be mutually commuting, we can either construct a commuting projective Hamiltonian, or equivalently to construct a stabilizer group, which is the group generated by all of the abelian group generated by all of these stabilizer operators theta. So in either perspective, this choice of the stabilizers gives a splitting of the Hilbert space to direct some of the code space with its complement. So this code space, or the ground state space of this Hamiltonian, is just the set of states which are stabilized by those operators in S. So in this sense, this describes an error correcting code, and that if this code space has some non-trivial dimensionality, we can store logical information in it, and we can correct for errors which correspond to violations of the stabilizer condition by just measuring the stabilizers and then locally correcting them. So that's in the sense in which we have an error correcting code. And what's important for us is that one can construct for any abelian topological order with gap boundaries an explicit stabilizer model realizing that topological order. So to be a bit more explicit, the exact correspondence between the error correcting code language and the topological order language is, so if you have an abelian topological order, it's specified by the choice of the different anyons, their fusion rules, and the braiding relations and the spins of the anyons. So in the error correcting code language, errors, which are a violation of the stabilizers, correspond to local anyon excitations. The stabilizers correspond to closed anyon loops, or in the symmetry language, exact one-form symmetries. And as I said, the code space corresponds to the ground states, and operators acting on the code space, but the logical operators correspond to non-contractible Wilson loops. So again, in the stored code example, where we have electric magnetic excitations and this dionic fermion, the stabilizers are given by, or the errors are generated by Z correspond to two electric excitations, which violate the star operator condition, and the X generates magnetic excitations, which violate the plaquette operator conditions. As you can see, the plaquette corresponds to a closed E loop, and the star corresponds to a closed M loop. And the rhetoric code encodes two logical qubits of information based on the non-commuting, non-contractible Wilson loops. And so I'm just emphasizing this language, since once we move to the mixed state setting, we're going to try to identify the new topological order based on the behavior of these based on the stabilizers and this Wilson loop algebra. So now that we have these topological orders, we want to try to couple them to an environment to generate interesting mixed states. So one way to do this, so rather than modeling this coupling to the environment microscopically, we'll take a more generic picture and think of the coupling to the environment as just being some quantum channel. So something which maps density matrices to density matrices. And such quantum channels can always be expressed in a so-called Krauss form, where these Ks are generic operators which satisfy this trace preserving condition. We're going to focus on local channels. So channels which can be written as a product of channels acting independently on each site I, which have the interpretation of incoherently proliferating errors or anyons in the theory. So for instance, in the stored code example, this local channel corresponds to creating with probability P a pair of E excitations localized near site I, and probability 1 minus P doing nothing. So what you want to think of this physically of this channel doing, once we apply it to a pure state topological order, is generating a classical ensemble of states in which we have pinned electric excitations randomly at each site in space. So this physical picture is somewhat suggestive in that it almost looks like we're condensing these electric excitations, but it's not quite that, since we don't have a quantum superposition, but rather just a classical ensemble of these states where we have these defects.
I can't think about this as a modification of the Hamiltonian.
In a sense, so you could think of this, I think, as, so you imagine you have like some random potential, which pins the electric excitations, and this is like the disordered ensemble, is perhaps one way to think about this. So there's like, in some sense, some inherent, I guess, randomness involved. So yeah, you could probably think of like an ensemble of random Hamiltonians mimicking this kind of behavior to some extent.
Maybe because it's not a unitary transformation on rho.
Yeah.
Not a unitary transfer. No, but
It is.
that's okay.
It's
I can still add couplings to the Hamiltonian.
not. I think not always.
Not
If it's
preserve
not,
unitarity.
well,
It's a
it
mixed
has to
state.
be then.
So you can imagine, say, embedding this in a larger space in which you have some unitary operator and then tracing out the environment, and then that will generate this state. So you could, consider a purification of this as well. But this particular classical ensemble would not be like the ground state of a specific Hamiltonian just acting on the system.
If you're familiar with Lindblad equation, this would be discretized version.
Oh, so I was thinking of adding Lindblad like couplings.
Yeah, but you cannot replace Lindblad couplings with modification of Hamiltonian, can you? For the same
I
reason.
thought you could model it as a
In the bigger
non-emission,
space.
as a non, in the biggest, including the environment.
Yeah.
In a including environment, yes.
Only. Am I misremembering? So I can't think about Lindblad just as deforming my emission Hamiltonian to something non-emission.
There is an extra term.
Part
You
of it,
can
yes, but there is
observe
an
part
extra
of
term.
the Lindblad to the Hamiltonian. There's another Hermitian term, but there is an extra term that conserves the trace equals one condition. So I think that term you can never.
You won't see from without including the environment.
Yeah.
Right. So basically, we're going to be interested in characterizing states of this form. So just as a bit of context as to why these might be stable, these error-corrupted stabilizer codes have been studied quite extensively. And so particularly in the context of this toric code, it's known that up to some finite value of P, the toric code topological order persists. So there's a few ways to characterize this, but most recently people study this by using mixed state entanglement measures of the mixed state. And it's been shown that there's a transition in these entanglement quantities at this non-zero value of P. So the expectation is for below this critical decoherence strength, we should have something which is just the toric code topological order.
In this case of the transition, can I think of it as like some sort of pseudo gap closing, or what is the theory that lives at that PC? Do people?
What describes the critical
Yeah.
transition? So I think there's like this random bond Ising model, which describes this transition. So in this, I guess in the original study of this, they're looking at when you can recover the logical information. And so you have, there's some effective statmix model, which describes these transitions. In this case, it's this random bond Ising.
But in the quantum context, what is sort of like the signature, or like, do people like know the exponents and stuff associated to this? Or because it's topologically ordered on this part, right? And it's somehow not. So
yeah, so I'm getting, so to characterize it based on the properties of the state, I think you need to use these in like entanglement measures.
okay,
So I think I'm not sure, but I think they've probably computed the critical properties.
Okay.
Yeah.
thanks.
But yeah, so the question then is, above this transition, whether what we're getting here is just completely trivial in some sense. And so what we're going to show for generic topological orders is that no, there's something non-trivial. In particular, we're going to focus on this fully corrected limit, which corresponds to maximal decoherence of these errors or anyon excitations, and construct something like fixed point models for these intrinsically mixed states.
Sorry, could you just clarify a bit the operation you're doing? You start with initial state and then you're gonna apply this quantum chain operation. This is like a unit, you're evolving time one step.
Right.
So there, at every I, you're evolving one step in time. But now what I'm confused about, like Zi, there is just the matrix sigma I at site I, right? So this is a unitary transformation. Why are you saying that this is non-Hermitian? What is wrong with this?
The Z's themselves are Hermitian, but the operation as a whole is still not Hermitian. So if you think about like, the Lindblad formalism, this would be like taking the jump operators to be Z.
Okay.
So it's like, yeah, you're randomly applying these unitary operations, and the randomness is in some sense what gives you the non-unitary property, I think. Yeah, that's one way to frame it.
Yeah, the limit P goes to 0 becomes infinitesimal Lindblad operator. Because P times rho is Z squared times rho, something like this. So this, right?
I see, okay. I see.
So the Hamiltonian is 0, but Lindblad operator is has jump operators which are Zi.
I see, all right.
Okay, so this is, in the context of just this toric code, but the general, so in the next 3 slides, I'll frame the general construction that we have, and then discuss some specific examples to make things a bit clearer. But the general setting is we're going to start with some generic topological order, just an abelian one for now, described by some anyon theory C, for which we can always construct some stabilizer model. We're then going to start with some state rho, which is in the code space of the stabilizer model. So it satisfies the stabilizer condition. And then we're going to subject it to one of these local error channels.
You only hit with this operator once.
Yes.
Right? So it's not like iteration of this, just once.
Yeah, there's no continuous time evolution, just one time step. So so we're going to have this local error channel, and the local errors, so these O's are going to be operators which create some anyon species A near site I, which is of order K. So the 1/K tells us we just have maximally incoherent proliferation. So at any site I, there's equal probability of exciting no anyon, 1 anyon, 2 anyons, and so on.
You're using the abelian and admits gap boundary condition when you do this.
Yes. So in the toric code example, O was just the Z operator and K was 2. So the goal is now to characterize the properties of this mixed state rho E. And to do this, as we did for just the stabilizer models, we want to understand what the stabilizer group of this, or equivalently characterize the one-form symmetries, which tells us about the anyon theory describing this state. So it's clear to see that the things that stabilize rho E are precisely the original stabilizers, but only those which commute with this error channel. So it seems like a pretty simple statement, but it belies a deeper structure. So as I'll show in the next two slides, this statement actually tells us that rho E lies in the code space of something called a subsystem code, and this exhibits this non-modular topological order I advertised earlier on. So this subsystem code structure just almost falls out immediately. Basically, the idea is we start with some, we define this group F, which is generated by the error operators on each site, and we define something called the gauge group. So this is something from the error correcting code language. This doesn't have to do with an actual gauge theory or the gauge group of that theory. This is defined as the group generated by the original stabilizers and the group F. So G is in general a non-abelian group. So then the statement that rho E is stabilized by these S's is just the statement that the stabilizer group of rho E is generated by the center of the gauge group. So as it turns out, this structure just immediately gives us the structure of a subsystem code. So I don't want to go too much into details of what this means in the context of error correction. The gist is that as in a stabilizer code, there's a splitting of the code, the Hilbert space into this code space specified by the stabilizer group. But the choice of this gauge group further splits the code space in something called the logical space, where we store information, and something called the gauge space, which is induced by this equivalence relation. So physically, what you want to think about is that in the original parent topological order, we had some set of logical operators or Wilson loops and stabilizers, and after we do this decoherence, some of them are projected out. So some of the errors become redundant in the sense that they only act within the gauge space, which means equivalently that the Wilson loop some Wilson loop operators have trivial commutations with every other Wilson loop operator. So in the anyon theory language, as I'll say a bit more explicitly, some anyons braid non-trivially with every other anyon in the theory. But this is precisely the structure of a non-modular topological order. So indeed, it's been shown previously that the subsystem codes you can construct a subsystem code which utilizes every kind of non-modular topological order. And the physical import of this is that it's believed that that you cannot realize a non-modular topological order purely in 2D. You have to get it on the surface of some 3D topological order. But we're getting this structure purely in a 2D mixed state. So just to restate what I said in more physical terms, not in the context of the stabilizer language, we started with some parent topological order C. You applied decoherence of A, which yielded some mixed state characterized by some other anyon theory. This anyon theory corresponds to all those anyons B in the original C, which braid trivially with the decoherent anyon. This is just restating the statement that the remaining stabilizers are the ones which commute with the error channel. And so as it turns out, this so-called centralizer of A or of C actually has a consistent structure of a braided fusion category, but just without this modularity condition. And so as I said, these kinds of anyon theories typically are realized on the surfaces of higher dimensional topological orders, specific lattice realizations given by these Walker-Wong models, if you're familiar with them. And so it's in this sense that we're claiming that these fixed point mixed states that we're generating are intrinsically mixed, and that we're realizing this, again, non-modular topological order purely in a 2D setting. Yeah, so is that more or less clear so far? Okay, so this is in essence, the main claim of our paper, that we can generate these intrinsically mixed states, and we can characterize them or partially classify them at least based on braided fusion categories. Yeah.
So could I try to play the same game? Now I don't worry about the admitting gap boundary or abelian condition, but I still have, let's say I have some generic unitary modular tensor category with some anyon that I guess it won't be modular in the beginning if there's a centralizer. But then can I just like decoher it with all of those guys and still get the
so far I framed it in the context of stabilizer codes because we can do things very explicitly and exactly. But this picture holds for just any topological order. So you start with some UMTC. You can construct the centralizer, and you'll get some braided fusion category at the end. So you can do non-abelian and chiral theories as the input as well in principle. So if there aren't any questions, just to be a bit more explicit, let me discuss this in the context of some specific models to emphasize some of the physics. So let's again return to this toric code example. So the topological order is given again by the E, M excitation and their dionic composite. And on the torus, we have the two sets of Wilson loops around the non-contractible cycles of the E and M excitations. So we again consider the local error channel corresponding to the Z operations. And we're focused on this maximal decoherence limit where P equals 1/2 in this earlier phase diagram. And so using the structure that I just outlined, so we don't need to worry too much about the structure of the subsystem code. The key point is that because this Z anti-commutes with the star operator, the stabilizer group of rho E will consist purely of closed loops of the electric excitation. But differently, this E decoherence channel projects out all the magnetic Wilson loops, but leaves behind unchanged the electric Wilson loops. So the anyon theory, which corresponds to this subsystem code, is precisely a non-modular topological order described by the so-called Z20 theory. So this supports just the vacuum and this electric excitation. So here, this is non-modular because the E is a bosonic excitation, and so it cannot detect itself since it's the only anyon in the theory. So it's in this sense where one can say that this purely decoherent state is still in some sense intrinsically mixed topological order. In some sense, it's still a trivial state since there's just a quantum memory. We can store a single or two bits of information in the two electric Wilson loops. And you can check that rho E is actually purely separable. There's no entanglement. It's a purely classical state. So to give it something a bit more non-trivial, we can focus again still on the story code, but instead try decoherence of the fermionic excitation. So we can do this by considering local noise generated by the so-called ZX errors, which you can check create fermionic excitations with some particular framing. And so if you just again plug in this information to the subsystem code, you can check that the stabilizers stabilizing rho E correspond precisely to closed Wilson loops of the fermionic excitation. And so if you look at the effect of the error channel on the Wilson loops, the electric and magnetic excitations are projected out, but these fermionic Wilson loops remain unchanged. So the topological order characterizing the subsystem code is described by something called the Z21 theory, which contains the vacuum and a single fermionic excitation. So what this decoherence has done effectively is project out all the electric and magnetic, say, one-form symmetries, and left behind just the fermionic one-form symmetries. So we peeled off all the bosonic data. And what's interesting is that this particular model was studied previously, as I alluded to earlier, where it's found that this state is actually still long-range entangled as measured by something called the entanglement negativity. So the state appears to indeed lie in some kind of distinct universality class from the Z20 theory I presented on the previous slide. And again, this is non-modular because the fermion has non-trivial spin, but has trivial exchange statistics with itself, so it cannot detect itself. So we can go a step further to get something a little more non-trivial in the sense that it has quantum memory by considering something called the Z4 toric code. So here we consider a 4-level system on each edge. And we construct similar plaquette and star operators as in the Z2 case. And so this exhibits a Z4 gauge theory. So the anyon excitations are E and M particles of order 4, satisfying these braiding relations. And we can consider decoherence of this E cubed M excitation, which is again generated by the ZX and Z dagger X type operators. And so the point is that not having to go through the subsystem code picture, we can just focus on the anyon theory in this gauging out picture. We find that the resulting non-modular topological order is Z41, which has these anyonic excitations. And the key point is that this E squared M squared excitation is transparent. It braids trivially with everything else. But these EM and E cubed M cubed excitations are mutual semyons. So here we have, again, a non-modular theory, but moreover, this has a mixture of a quantum memory with 2 qubits generated by the EM and E cubed M cubed excitations, and a classical memory generated by the 2 Wilson loops of this transparent anyon. So this is, again, something beyond just the modular topological order we get in 2D. So hopefully that gives us the general picture of this construction. The last example I want to discuss has some interesting practical applications. So the idea is we start again with some abelian theory, in this case, a double semyon theory. So this consists of a theory with a chiral sector, so a semyon S, which has a spin of I, times the time reverse conjugate. So the S bar has the opposite spin. So overall, this theory is non-chiral. It has gapped edges. But we can, and one can construct, so yeah, one can do all this analysis in the stabilizer language, but let me forgo that and look at just the anyon data. We can decohere this S, so we can decohere this S bar in the theory, which has the effect of just projecting out the one S bar part of the theory because S bar breaks non-trivially with itself. And the result is a purely chiral semyon theory. We projected out this one S bar part. So this is, pretty cool, I think, in the sense that this has a practical implication that we can think of non-chiral topological orders, which have a factorization into a product of two modular theories, which are independently chiral, and apply this decoherence process, treating these as resource states to generate mixed states with chiral anyon data. And so this goes beyond standard measurement plus feedback protocols, as far as I understand, which typically can only produce topological orders with gapped boundaries. And the second point, which will be clear on the next slide, is that all these density matrices that we constructed are in some sense fixed points. So as we'll see on the next slide, if we consider the vectorized density matrix, we'll see that it corresponds to some stabilizer code in some enlarged Hilbert space. What this tells us that there should correspond some exact projected entangled pair operator description for these mixed states, which is surprising for people familiar with this tensor network literature, and that it's generally expected that pure chiral states do not have a TEPS representation. So this suggests that we can capture chiral theories in the context of tensor networks for density matrices. Yeah.
Just to clarify, I think when you say you've realized a certain kind of topological order in a mixed state, what does that actually mean? Like, can you say again, what is the, when you say it realizes this kind of topological order, what does that mean? Like, what's the definition of a mixed state realizing a particular kind of pure state?
So in this language, we're saying that rho E is stabilized by those stabilizer operators corresponding to that anyon theory. So in the sense that if you look at the Wilson loop algebra, say, it exhibits the same braiding relations as that corresponding topological order.
And how are Wilson loops defined for a mixed state?
So in the same sense of as they would be for just a pure state. So you're checking that rho E is stabilized by those Wilson loops.
So any operator that preserves the state qualifies as a Wilson loop, or does it have to be? I would think you'd, like, in regular topological order, you have more conditions than that in some sense, right? You also need the fact that, well, anyway, I don't want to derail your talk, but just having an operator that preserves the ground state doesn't mean it qualifies as a Wilson loop, right? Or Wilson line operator. Like, you need the endpoints. You kind of need it to be unbreakable somehow. Like, if you break the Wilson loop, you have an open line, it creates two excitations which can't be destroyed by any local operation, right?
Right.
I'm just, yeah.
Right. Yeah, I guess maybe we should discuss a bit more deep. Yeah. Yeah, so these are the, I guess, essential examples describing the, yeah.
I have a question about the first point here, which is there a way to actually engineer such decoherence in like any quantum platforms, like physically, or?
So I think one thing that they do, like in Google, so you can perform like measurements of Z, but you just don't keep track of the measurements. So that
you'll measure the S bar guy and then like delete information.
Yeah. So for wrapping up this first part, I just want to present briefly a slightly complementary picture to the staging out procedure that I have outlined. So the idea is that when we're dealing with density matrices, it's often convenient to vectorize them using this Choi-Jankowski isomorphism. So basically the idea is you start with the density matrix and you flip the bra into a ket. This defines a new state rho on this double Hilbert space where H plus and H minus are just copies of the original Hilbert space. And so the idea is that if rho described something in the code space of a topological order C, then this doubled state corresponds to a bilayer topological order with the topological order C on the Ket space and the time reverse conjugate on the H minus space, the bra space. And one can check that this rho E, the decoherence process, precisely corresponds to doing anyon condensation of A plus A minus in this double Hilbert space. And so it's known that if you start with a bosonic topological order and do this anyon condensation procedure, you get back just a modular bosonic topological order. So that tells us that this vectorized density matrix has some stabilizer description, which sort of motivates that last point on the previous slide, that we have a stabilizer description for the density matrix, and hence this corresponds in some sense to like a fixed point state. So just to conclude this part of the talk, what I tried to argue is that we can generate intrinsically, in some sense, intrinsically mixed state topological orders by applying these certain decoherence processes to parent topological orders. And so this generates states which are characterized by non-modular topological order and can in a sense be thought of as sort of exfoliating surface states of some higher dimensional topological order, in the sense that as pure states, these states can only be realized on the surfaces of higher dimensional theories. And so this leads to a partial classification of these density matrices in terms of braided tensor categories. And in some loose sense, we expect these to still correspond to phases of matter insofar as the fact that we're characterizing these states based on one-form symmetries, which, again, in some sense, we expect to be robust to perturbations. So there aren't any questions about this part of the talk. Move on to the second part.
So here you decohere certain anyon at the maximal strength, right?
Yeah.
So if I decohere not at the maximal strength, but maybe above some threshold, can you still define a notion of topological order?
Right. So I guess the perspective is that we're looking at these fixed points. So I think as you tune away from the maximal strength, you would expect like the corresponding Wilson loops to fatten out in some sense. So there is, but there's this, there's an order parameter that you can compute, this like WF order parameter. I guess we can talk in more detail later, but that's still able to detect, I think, topological order away from like a fixed point topological order. So yeah, we haven't fleshed out in detail what the topological order looks away from these fixed points, but there should be still, we expect it to still be able to characterize it in that way. So particularly in the Z20 and Z21 cases, the phase diagram for this toric code subjected to Z and ZX errors was computed in this previous paper. And they found those two phases to be robust in the sense that you can define them in terms of the classical memory they support. And in particular, the Z21 order exhibits a quantized topological negativity. So yeah, there's a few diagnostics we need to do to fully flesh out the extent to which these characterize genuine phases. At the moment, the most concrete thing we can say is that we're characterizing these fixed point density matrices. Are there any other questions? If not, I'll just try to speed through this second part of the talk. So we're going to change gears a little bit. So far we've been talking about starting with some specific pure state characterized by some structure and subjecting it again to a particular decoherence channel, which breaks, say, the symmetries of the initial pure state to get some interesting mixed state. So here I want to extract or generalize a bit and consider not any specific initial pure state or steady state, but see the extent to which we can characterize just this open system dynamics. So in particular, a natural question to ask is how quickly in an open system evolution one relaxes to the steady state. So particularly if you're trying to prepare some, say, resource state through this dissipative evolution, you would want to relax as quickly as you can. But if you're starting with some interesting initial pure state, you might want to delay the approach to the steady state. So that's the basic question you want to ask about these open system dynamics. So the question is whether you can make general statements about this kind of process And what I'll try to show briefly is that we can, again, appealing to this notion of symmetry. And what I'll show is that we can write down certain so-called Lieb-Schultz-Mattis type constraints, which allow us to constrain the spectrum of the generator of these dynamics. So to do so, we're going to focus on a particular class of open system dynamics called Markovian dynamics. So this is dynamics in which the bath is effectively memoryless. So this is to say that the time evolution of the system density matrix depends only at the state of the density matrix at that same time t, not at any previous times. And in this case, it's known that the time evolution of the density matrix is generated by a superoperator called the Lindbladian. In the same way, heuristically, that unitary evolution of a pure state is generated by a time-independent Hamiltonian. And so the evolution of the density matrix is described by this master equation, which consists of two parts. The first describes coherent evolution of the mixed state, where you can think of this H as being like a renormalized Hamiltonian for the system. So in the previous part, we just set this H to 0. And the second part describes the dissipative evolution. So these LNs correspond to jump operators, which are things that couple the system to the environment. The key point from this slide is just that when we think about Markovian systems, we can constrain the dynamics of the system by focusing purely on the spectral properties of this Lindbladian superoperator. And so explicitly, to do so, it's convenient again to switch to this vectorized picture using this Troy isomorphism, in which the Lindbladian becomes just like a non-Hermitian Hamiltonian in some sense. And we can diagonalize this Lindblad operator, which will generically have a complex spectrum. The key points are that the eigenvalues will always have negative real part since we have decay of the system. And there has to be at least one zero eigenvalue, since the system has to decay eventually to some density matrix due to trace preservation. What's important for us is that an understanding is this delta dg, the dissipative gap. So this is the value of the smallest negative part, the largest real part of the non-zero eigenvalues. The point being that at asymptotically late times, this dissipative gap sets the decay rate of the system to the steady state. So in particular, what we're interested in understanding is the scaling of this gap with the system size. So particularly, if this delta dg remains finite in the thermodynamic limit, we expect that the system decay rate decays exponentially fast with the system size. But if we have a gapless spectrum, then the system should decay algebraically fast with system size. So the first is faster decay, the second is slower decay. So understanding spectral gaps in many bond systems is difficult in general. And in particular, in this open system context, there is fairly limited results on understanding the scaling of this dissipative gap. The two results which are present, which are important for us, are for the Ising model with decoherence and the XXC spin chain with decoherence. Where in the first case, it was found that the system has a gap spectrum, whereas the second is gapless. So this is interesting because the difference between these two models is the fact that the second still has a robust U1 symmetry. So this gapped versus gaplessness is reminiscent of the behavior of the gap just in the closed system, where we know that the gaplessness of the XXC spin chain is enforced by certain non-perturbative constraints called Lieb-Schultz-Mattis type theorems. So just to quickly review those, the general idea is that these LSM theorems, in the most general phrasing, are dynamical constraints coming from some kinematic input, so imposing some symmetry on the system. So there are different generalizations of these, but the one relevant for us for the moment is a generalization of the original LSM constraint, which gives us some so-called filling constraint. So the statement is that a 1D Hamiltonian with translation invariance and a U1 symmetry in the fractional filling sector cannot have a unique gapped ground state. So the quintessential example is the XXC spin chain, where depending on the Ising coupling, we either get a doubly degenerate ground state or a gapless spectrum, which satisfies this theorem. So the question then is whether we can extend these kinds of non-perturbative results to this open system setting. And our claim is that we can. So to do so, we just need one more piece of information, which is to understand how symmetries behave in the context of these open systems. So the idea is that, expect that in a mixed state, rather than having exact symmetry, you could have a symmetry which in some sense hold just on average. So explicitly, what this means is, say we have some Lindbladian with and some symmetry group G, the unitary representation of some element in the symmetry group, we can impose a strong symmetry by saying that the Hamiltonian and the individual jump operators commute with UG. In this double space picture, this tells us that we have independent symmetry operators or independent symmetries for the broad cat spaces. And so physically, you can think of this as saying that the system has, so if G is a continuous symmetry, the system has some conserved quantity which does not leak into the environment. We can impose a weaker constraint called weak symmetry, which has this form, which in the double space picture tells us that we have just this diagonal action of the symmetry group on the broad cat spaces. And so one sufficient but not necessary condition for this is if the system plus the environment are symmetric under this symmetry, but not the system on its own. So this is naturally a weaker condition. So in particular, in the context of this XXZ spin chain with this SZ decoherence, you can see based on these definitions that there's still a strong U1 symmetry. So there's independent U1 symmetries for the broad cat spaces, but there's only a weak translation symmetry because the translations permute the jump operators. So we can see that this is, in some sense, slightly less symmetric version of the Hamiltonian system, which had strong U1 and translation symmetries. So the question is whether we can still extend this LSM theorem to this setting. And our claim is that we can. And the argument follows essentially the same logic as Oshikawa's argument via flux threading. So the idea or the statement explicitly is that a 1D Lindbladian with weak translation invariance and strong U1 symmetry at fractional filling sectors for the broad cat spaces cannot have a unique gapped steady state. So the idea is, suppose we do have a gap, then we start with, say we have a unique gapped steady state rho naught, then we can insert a 2π flux of one of the U1 symmetries for either the broad cat space, in this case just the cat space, which after the 2π flux insertion should give us back another steady state, since the Lindbladian should be equivalent to itself up to some gauge transformation. And following the usual reasoning of Oshikawa's argument, you can check that this gauge transformation is given by this twist operator, which one can check does not commute with the weak translation symmetry, but instead gives this phase factor. So this tells us that after this adiabatic insertion, we've had some spectral flow, and we've mapped to a new steady state of the original Lindbladian, which differs in weak momentum, which is non-trivial if we are at fractional filling. So either we have multiple determinate steady states, or we have a violation of the adiabatic assumption, telling us that we in fact have a gapless spectrum in the thermodynamic limit. And so that this is actually concludes the argument for this generalized LSM theorem, which again essentially just follows that of Oshikawa's argument. So to motivate this, we can do a bit of numerics and some specific models. So we consider this decoherent XXZ spin chain for spin 1/2 and spin 1, looking at the SZ equals 0 sector, which corresponds to half filling and integer filling of the U1 symmetry. And here is a plot of the real parts of the spectrum as a function of the flux for the U1 flux that we insert. So you can see that in the 1/2 case, there's a spectral flow of the Lindbladian eigenvalue into the bulk, which implies that there's a violation of this adiabaticity assumption. And so in the thermodynamic limit, we expect that the state is gapless. In contrast, in the spin 1 case, there is no flow. There's a well-defined gap. So this is doesn't show, but is at least consistent with the statement of the theorem that we don't necessarily have an enforced gapless structure. So this gives some evidence in favor of this LSM theorem. So
how do you impose like A, how do you compute this, and B, like how do you impose a filling constraint on the Hamiltonian?
So the filling constraint is you just you diagonalize that Lindbladian within that fixed sector because U1 is a good symmetry.
Yeah.
And then here so the flux is just you're inserting like twisted boundary conditions effectively.
You just did exact diagonalization of these. And how big were the?
These are small because when you do this double Hilbert space, you're doubling.
Yeah.
I think this is maybe 6 or 8 sites.
Okay.
So you can take that as it is.
So I think for Ishikawa's original argument, you can do adiabatic flux insertion since the twisted Hamiltonian is still a Hamiltonian. But here, if you do like this adiabatic flux insertion, the twisted Lindblad is not a Lindblad anymore, right? So here, how to justify this adiabatic flux insertion?
Yeah, so yeah, I think it still needs to be developed more rigorously how to justify this adiabatic assumption. We're just assuming that as long as there is a dissipative gap, then there is that the process is adiabatic. But yeah, there needs to be more justification for that. That's basically at the level that we're making this argument.
And also, since here you have a continuous symmetry, right? A U1 continuous symmetry. So I would expect, even if you have like integer fitting or like spin 1, since you could have diffusion that always take polynomial time, right? So I would still expect if you have spin 1 or integer fitting, the dissipation gap is still vanishing for sufficiently large system size.
Well, I guess that would not be inconsistent with our statement in the sense that you could still have a gapless structure here, but it's just not enforced by the LSM theorem, at least. Yeah. So in particular, I mean, so if you look at the full spectrum, not just in this S equals 0 sector, you'll see that it looks like you have a gapless spectrum as well. But yeah. So this discussion was for this filling type constraint, but the general picture I just want to convey is that if we start with some LSM theorem, which assumes translation symmetry plus some strong internal symmetry, we can obtain a corresponding LSM theorem for these open systems, provided the internal symmetry remains strong and the translational symmetry is just reduced to a weak one. So in particular, as we show in our paper, for bosonic systems, it's known that there's an LSM theorem, where there are LSM theorems which just require that you have a projected on-site representation of some internal symmetry. So for instance, Z2 times Z2 for spin 1/2. And one can show that using just the same kinds of arguments that you obtain corresponding LSM theorem, provided this Z2 times Z2 symmetry is still a strong one. Just to mention quickly, this argument breaks down if you have a weak U1 symmetry, since you have to insert U1 fluxes for both the Ket and Bra spaces. So the two phase factors cancel out. So you don't get a constraint if you have weak internal and weak translation symmetry. So that's just to motivate this statement. But there are also corresponding LSM theorems you can prove for fermionic systems, assuming strong fermion parity symmetry and weak Majorana translations. I don't have too much time to discuss, but there's also a unique symmetry in the context of these open systems called Kubo-Martin-Schwinger symmetry, which has some flavor of fermion parity symmetry, which again allows us to make some constraints about, make some statements about LSM constraints. But yeah, I can discuss this with people who are interested at a later point. Yeah.
So just quickly, the theorem or the argument you gave involved the continuous symmetry insertion of flux. How do you do something that's discrete like you have?
Yeah. So I guess there's two statements. So one is, so in that usual Hamiltonian context, the way that this is argued using twisted boundary conditions is, so say you have spin X and spin Z flips, you insert twisted boundary conditions, which, so you twist the boundary conditions by Z. The twisted system now has a modified translation symmetry, which is translations up to a transformation by Z acting on site 1. That modified translation no longer commutes with the X flip symmetry. So so that implies a degeneracy in this twisted sector. So I guess at a heuristic level, the claim is that if the system is sensitive to the spectrum is sensitive to these local twisted boundary conditions, the original untwisted sector should also have some degeneracy. That's made a little more precise in a paper by Oshikawa.
Is there a version where like, can you get more if you demand also weak, strong translation symmetry, or doesn't have?
So you can't get strong translation symmetry in general with just local Lindblads, right? Because if you just have a Lindblad or a jump operator acting on one site, then translation will necessarily permute you to a different one. So you'd have to have like all-to-all interactions in these jump operators to get strong translation. So in general, any like spatial symmetry, as far as I know, is reduced to weak symmetries in the context of these Lindblad systems. Yeah. Okay, so I'm out of time more or less, but I'll just state quickly that so in recent years, it's been understood that these LSM type theorems can be understood as being quantum anomalies. So explicitly, that's to say that there's some obstruction, even at the lattice level. That's to say there's some obstruction to gauging, say, the internal symmetry in the presence of this translation symmetry. So yeah, I won't go through the details of the construction, but I'll just say that you can also frame the LSM constraints that we've discussed so far in terms of anomalies of partition functions defined for these open systems. So you could think of, so again, basically the idea is you just have to construct some analog of the partition function. So one thing you can consider is the Schwinger-Keldysh path integral. Here we consider something called the dissipative form factor, which is just a trace of this time evolution in the doubled space. And basically the statement is that you consider this partition function in the presence of a weak translation symmetry defect. So you just twist by inserting the translation operator in the trace, and you insert a strong U1 spatial defect. So you insert twisted boundary conditions. And the statement of the anomaly is that if we restrict to one of the charge sectors and we perform a transformation, which would just be a symmetry transformation in the presence of these defects, we pick up some phase factor in this form factor, which can't be canceled by counter terms if the filling fraction is fractional. So this is, in a sense, a formal rewriting of this flux insertion argument. And the claim is that we should interpret this LSM theorem as corresponding to this kind of anomaly of this dissipative form factor. So that's in some sense, that's, yeah, maybe a slightly more formal sense in which these constraints should be considered robust. Right, so I guess I'm out of time. So I'll just say, and just to summarize, what we did in the first part was characterize a class of mixed states, which we claim to exhibit something called intrinsically mixed state topological order, which could be classified, partially classified based on brain diffusion categories. So there are several natural questions to ask in this context, like what the entanglement structure of these states are to further characterize them as phases matter. And as I claimed, we can interpret these intrinsically mixed states as corresponding to realizing surface states of a higher dimensional theory in a 2D mixed state. So it's natural to ask whether we can apply this procedure to exfoliate anomalous 3D surface states of, say, 4D theories. And in the second part, I argued for LSM type constraints on Markovian open dynamics. And a natural question is to ask is, so we constrain these properties of the spectrum, but one wants to ask, say, for instance, whether we can also derive constraints on the steady states themselves, which we were not able to do. But yeah, the broad sort of message, I guess, is that we can make use of tools and techniques that we have from many body physics to sort of carve out the space of dynamics and states that are sort of intrinsic to the mixed state setting. So with that, I'll thank you for your attention and open up to any further questions.
So for the ones that are not modular, are there more interesting like linking configuration like Borromean rings or something that can detect the fact that you still have something that is topologically non-trivial?
Yeah, I'm not familiar personally, but it's an interesting question.
I guess operationally, how would you go about, like, let's say I just hand you one of these non-modular topological orders, like what would you do to like know that you had something that was topologically non-trivial?
Like, yeah, what kind of braiding operations?
Yeah, exactly.
Yeah, I guess operationally, I'm not sure how you would identify.
So you still get the degeneracy on non-trivial.
You still get the degeneracy. I mean, you could compute like the different pieces of data that characterize the the non-modular theory, but yeah, I'm not sure if there's a specific operation you could do to say that you have a non-modular theory versus a modular.
So here by degeneracy, you mean a degeneracy of what? Since you are just dealing with states, you don't have a Lindblad or Hamiltonian. So you mean by degeneracy, what kind of degeneracy?
So I guess in the sense that if you think about, so in the context of starting from the parent theory and then projecting down, we start with some code space, then code some logical information. And I'm identifying that like logical space with the word degeneracy. So when we decohere down to this intrinsically mixed state, there's some reduced logical space. So yeah, by degeneracy, degeneracy is maybe the wrong word, but it's in terms of the amount of like logical information you can encode in this density matrix.
By the way, we are out of time, so those people who want to leave can leave and others can stick around for questions. Raman will also be here until tomorrow evening. Feel free to catch him. He's in the visitor's office on the third floor.